Hello and welcome back to day 15. You'll notice that we skipped a few days. That's because those days weren't interesting algorithmically in terms of showing off TDD techniques. In fact, they were mostly frustrating. One case, for example, you need to know how to do linear algebra. So hopefully you have studied up on your linear algebra and you were able to do that day. But today, not linear algebra. So let's go ahead and let's get started. Day 15, Warehouse Woes. Okay, so Vasco of Lanternfish. They seem quite anxious. They need a lot of food. Food needs to be stored somewhere, so they have complex warehouses. Great. Anxious because they have lost control of the robot that operates one of their most important warehouses, currently running amok, pushing around boxes in the warehouse with no regard for logistics or inventory management strategies. Right now, none of the lanternfish are brave enough to swim up to an unpredictable robot, so I could shut it off. However, if you could anticipate the robot's movements, maybe they could find a safe option. So they have a map of the warehouse and a list of movements a robot will attempt to make. Problem is, the movements will sometimes fail as boxes are shifted around, making the actual movements of the robot difficult to predict. So here is our map. So as is typical for these things, this indicates, walls, immovable things, and, or a pillar, for example. And our robot here is the at character, and our boxes here are the O characters. These movements, pretty obviously, left, down, down, left, up, left, down, up, right, down, right. Okay, so big list of movements. So, as the robot attempts to move, if there are any boxes in the way, the robot will also attempt to push those boxes. However, if the action would cause a robot or a box to move into a wall, nothing moves, including the robot. Initial positions of these areas are shown. So the rest of the document describes moves for up, down, left, and right. The robot will attempt to make an order. The moves form a single giant sequence. They are broken into multiple lines just to make copy pasting easier. New lines within the movement sequence should be ignored. Here's a smaller example. And this is where we're actually going to get started test-wise with this smaller example, because they very helpfully give us exactly what happens in each step. So let's quickly review this, right? So here's our small warehouse with a couple of pillars, in a square, and looks like 6 boxes in our robot, and a relatively small amount of moves. So this is our initial state. Tries to move left, can't do anything. So you can see that these two states are exactly the same because you can't move into the pillar. Moves the robot up. Tries to move up, that's the wall, can't move through a wall. Tries to move right. You can see push these 2 boxes now together. And when he tries to move right again, both of those boxes move. Okay, so our movement system is going to be some kind of recursion because we can push multiple boxes at once with a move. So again, tries to move right. This time the boxes are sitting against the wall, so can't go anywhere. Tries to move down. You can see he moves the whole stack of 4 down with him. Tries to move down again. Nothing happens. Moves left. Moves down. Moves right. Moves right. Moves down. Moves left. Moves left. Can't move. So they've given us this set of 1-by-1 steps, really well illustrated. So here's what we're going to do. We're going to try to take this and implement our robot moving algorithm. Okay, so that's going to be our first set of our test data. And then for the larger example, which is all the way up at the top, they basically just give you the end state. They say, hey, if you can run all those moves and your thing looks like this, then fantastic. Then you're good to go. So we will also use that as one of our pieces of test data. So the last thing we need to do is they are basically giving a score for every box. It's based on GPS coordinates. But in essence, it's 100 times the distance from the top edge of the map plus its distance from the left edge of the map. This process does not stop at wall tiles and measure all the way to the edge of the map. So for example, this is in 1,4 because we actually do come down 1 from the wall and over 4 from the wall. So 0, 1, 2, 3, 4. So that's 104. And so they're looking for, once all the boxes are moved, what is actually the GPS score. So we will be doing that as well. But like I said, the first thing we're going to do is we're going to take this, and because we have all of our intermediate steps, we're going to do these things one at a time, and we're going to see how it works out. So as is our norm here, we're going to make a grid class, and we're going to make some, actually, what do you want to call this? We don't want to call it a grid. That's boring, right? Storage room. Okay. Storage room tests. And the first thing I want to do here is I want to have this. And this is going to be our input, right? And then what I think we want to do is basically say, what does the room look like after we have taken all of those steps? So this is what the room should look like when we're all done. So we're not going to be concerned at the moment with the GPS stuff, right? We just want to get the movement operations running correctly. That's going to be our first concern. So here we have the starting position and the movements that we want to take. And then what should the board look like when we're done? As we mentioned here, the one left, the board's going to look exactly the same. So public void movements show new board. Okay, so this is going to be our input, and then this is the expected room when we're done. So our storage room is going to take the input, right? So let's say var storage room is new storage room of the inputs. But we don't necessarily want the whole input, right? The storage room doesn't really need to know about this movement here, right? The storage room could literally just take this information, and it doesn't need to understand movement because we're going to, the storage room is going to allow us to move things as we wish, because that'll be the easiest way for us to test this out. So I think, actually, you know what? I changed my mind. Let's go ahead and have the storage room contain all the movements as well. So that would mean our form movements, right? And then cert equal storage room. We'll say that the storage room can toString itself, and that we should get the expected room back out of the storage room. Okay, so that's it. That's our starting point. We'll do the storage room perform movements. Okay, so we need a constructor. All right, so let's make the storage room constructor. There's our input. We need perform movements, right? And then we override toString, right, to return all the things here, right? So if we run that test, obviously that's going to fail because we expected to get this thing and we got this thing instead. You can see we have positional stuff going on here. We've talked about this in the past, but just in case you've missed it, our assert equal for strings tries to help you with positional stuff to say, by the way, I was here when I found the first difference. But you can see that our string gets cut off, and you can also see that our new lines are being formatted here. So maybe what I actually want to do here is use assert equal and say, don't treat this as a string, treat this as objects. Okay, and now when I run that, we'll see, here's our board, and here's this. Normally for me with strings, you know, I like the way strings work, but this object, you know, way to hop out is going to be much more easy for us to visually look at. Yeah, so there we go. So we need to get this stuff working, right? So we know we're going to need the grid, right? We know for sure we're going to need the grid. We're going to need to know where the robot is, right? So row and column, where's the robot currently? We're going to need to know the list of all the instructions, right? So here's all the instructions. That's the stuff we're going to pull out of this input. So the first thing we're going to need to do with this input is we're going to do a pieces split we're going to split on environment new line, right? And the grid is going to be equal to, oh, I got up there, input, yes, we're going to say input, no, piece is 0, right? And then we're going to split those on environment new line, right? And then we're going to say pieces sub-0, input split. Right. So we'll split that on new lines. Oh, no, actually, that's not what we wanted. Split on new lines. Split on new lines. Yeah, no, that's fine. This isn't pieces, this is lines. Okay. What we need is the split index, and that is lines, index of environment, index of an empty string, right? So we're looking for that blank line. This needs to be a list so that we can get index of. There we go. All right. Brain kicking back in. So we do lines from 0 to split index. All right, that's the top half. And then for that, we're going to want to select. So for each row, we're going to turn that into a character array. And then we're going to turn the whole thing into an array. All right, so that should give us our character array. Now, the other half is the instructions. And we were told that the instructions can be on multiple lines. And we can ignore the new lines. So that means what we're actually going to do is we're going to string join the lines from split index +1 to the end. And we're just going to join those with a blank. And so that will undo the split we did up here on new lines. So given that, we're just going to turn that into a character array. So easy enough. That'll give us our instructions as a character array. So the last thing we need to do is we need to find the robot. So we'll write the loop we have written so many times this year. So row is 0. Row is less than grid length. Double plus row for column is 0. Column is less than grid. Row length. Double plus column. And then if we will also write our famous get node, because that's how we try and make sure we don't go off the edges of things. So get node of row and column. If you're the @ then the robot is row and column. Okay, so we know we're going to need our get node. So this is going to be this. Actually, I'm going to do something a little different. We've been returning null, but in this case, null and the wall material effectively work the same. So instead of returning null, we'll return wall material if you're off the edge. Okay, row and column. If row is less than 0, or row is greater than or equal to grid length, or column is less than 0, or column is greater than or equal to grid row length, you're going to get wall material. Otherwise, you're going to get grid, row, and column. Okay, easy enough. So that's going to be our parse. Let's still go ahead and do the toString, because the toString is obviously the inverse of this, right? And so we'll use our loop here, right? Our result is a new string builder. We'll use our loop and we'll say result plus equals, or result dot append the character, which is a get node of row and column. Right, and then we need a new line after every one of these, result, append, line. And then return the result. So even though we haven't done anything for perform movements, this should be enough for us to actually pass this first test, because of course this movement does nothing. Right, so let's make sure that that's going to work. And we've got an extra new line here at the end. That's not a problem. We can trim that out. Well, instead of using a string builder, the easiest way to trim this out, let's do this. Let's do string join with environment new line. The grid select row, and then another string join with blanks the row. I think that'll get us what we want. And then it's just one nice piece of code there. Okay, now our test is passing. So yeah, so we didn't have to do this loop, right? We're going to go ahead and let the select do our loop for us, and then the string join will do the outer loop for us. So there we go. So first one done. Easy peasy. We didn't have to do anything yet. So if we take one more move, right? Now, if we take one more move, that's going to be this. And then our next one is going to be this. You know, this is going to be our result. So I wish I could figure out how to tell Visual Studio to stop messing up my pastes. So after the second move, we will have moved the @ sign up a space. Okay. Now we expect this to fail because, of course, we have not we've not actually implemented the move yet. So you can see we expected the @ to move up, and the @ is still sitting here. So let's go ahead and now implement the movements. So the instructions are the list of things we're supposed to do, and we always execute those instructions from the point of view of the robot. So we're going to do for each var instruction, and instructions. Now we know that the boxes move together. So the robot can push as many boxes as possible as long as there's someone somewhere to push them to. Right? So as long as the boxes aren't going to run into an obstruction, meaning the wall, because really the only thing they can run into is the wall, right? We've got walls, we've got empty space, we've got boxes, we've got the robot. Boxes can't run into the robot because the robot is pushing the boxes away from it. So we're really only worried about running into the wall. So the easiest thing for us to do here then is, with a recursive algorithm, is basically we're going to try and move every box that's in the way, right? So the robot will see the first box and say, okay, that's a box. I'm going to try and move that box, right? And then that box says, okay, I want to move, but there's a box in the way. And we just keep going down and down and down until either the box is going to hit a wall, in which case I think my camera just did something weird. Let me do this, because I think that's what it did. It's trying to track me. Okay, good. Because either the box is, I gotta watch my hand gestures. Either the box is going to hit a wall, in which case nothing works, or the box hits an empty space, in which case everything cascades all the way up and we're able to move everything. So that to me says recursion. So we'll do if we need to try to move. We're going to start with the robot's row and the robot's column. We need to know which way it's going, so drow and decol. And if you're able to do that, then the robot is now in robot row plus drow, robot row plus decol. So that's basically us just keeping track of the robot. And we're assuming that try move here is going to manipulate the grid so that when you have a successful move, it will actually move all the data for us, and move all the character notations for us. So we need to know what direction we're going, and that's going to be based on the instruction, right? So we need a list of directions. So we'll do a dictionary from character to int drow decol. All right, we've done this before, so we need a new one of these. And what we want is left goes 0, -1, right? And then right will go 0, 1, right? And then up will go -1, 0. And then lastly, down, they use a lowercase v for, we'll go 1, 0. Okay, what have I done wrong here? New, dictionary, new, okay, new. This looks correct. Oh, yeah, I didn't give it a name. I'm like, it's really upset about something and it shouldn't be. Okay, so that's directions. So we need to know what direction we're going in, right? So var drow decall is directions sub instruction. That's the last thing we need to know is where are we going? We have not implemented try move yet, so let's go ahead and do that. And we need to know if it was successful, right? So we're going to return a Boolean. And so we've got row, and we've got column, and we've got D row, and we've got D column. Okay. So it doesn't really matter where we are, because that's not what we're curious about. We want to know where we're going and whether or not that's movable. So we'll say this is our adjacent item, right? So we'll get the node at row plus D row and column plus D column. And this is recursive. So what's our exit case? Our exit case is if the adjacent is a wall piece, then we stop, right? That's the only thing that stops this algorithm is you're trying to move whatever is at row and column into a wall, and that's not allowed. Okay. So the obvious thing then is if we're going to be able to move this, then we actually have to move it, right? So actually moving it would be, we would take, we would say the grid at row and column is now a dot, right? Because we're putting an empty space there. And then we're going to say grid at row plus D row, column plus D column is, oh, actually, we need to know what we are. Yeah, we need to know what we are, because that's what's going in this place. Okay, so we don't actually care what's adjacent other than to test it for its negativeness, right? So this is pretty simple, right? We say if it's movable, we move it. If it's not movable, we don't. So I think that should be enough for us to get going here. So let's go ahead and run this test and see where we are. Okay, we're in pretty good shape. All right, let's do one more simple one. Right, so now if we take this, let's do 4 steps worth. Let's actually do 5 steps worth, because that's going to move, or all 6, right? That's going to move all the O's over here. And it's also going to push the O's against the wall and be not movable. So that's a pretty good test to make sure that everything is moving correctly. We haven't actually started pushing anything yet. That should get us to understand whether or not our pushing is working. So that's our next data, inline data. That's this, and we're going to move it 3 to the left. All right, and then we need the end results. And our end result over here, after 1, 2, 3 pushes to the right. So you can see this one, right? First push to the right gets it next to the box. Next, yeah, pushes the box that was next to it, next to the next box. The next move pushes both of those boxes against the wall, and the third move doesn't push anything. That's what we want. We want it to end up there. Okay, so we didn't. Why not? That's a good question. Looks like we are somehow not tracking some of the characters. All right, so I guess we took too big a step. That's fine. We'll go ahead and skip this for now. Skip is soon. Let's go back and get a smaller step. All right, so the next step would have been this one, which would push the boxes together. Let's do that. See if that helps us figure out where our bug is. All right, so that's going to push our stuff together. So that should give us the first right. That should give us this. Let's make sure that is working, because that's going to push the box. Okay, let's see if we can figure out what's going on here. Okay, so we successfully moved this thing there and didn't move this thing there, so we're missing our recursion. Okay, that makes sense, because we never actually recursed, right? We need to know whether or not we can move the next thing. So what does that mean? Well, if the adjacent is dot, we know we can move it, but we didn't take into account the fact that a box could be next to a box. So the thing we can try and do then is we can try and move the box that's next to us, right? And then column plus d column with d row and d column. And if the space is empty or we were able to move the next box, then we do this. Otherwise, we weren't able to do it because something downstream said we couldn't do it. So that's what we were missing. Okay, so we run that, and now we're good. We can probably unskip this one down here. And that should probably be good now. Okay, so that's good. I feel like the last two tests we're going to do then, we'll go ahead and do this whole thing, right? Because I feel like we have everything, sort of laid out now. I think we've hit all of our edge cases, so we're going to do the whole thing. And we're going to look for the end state. Right, so our end state is all the way down here at the bottom. That's this. Will we end up in this end state? Let's find out. Okay. We did not. Did I? Okay, hang on. That's very strange. I thought we were done, but apparently we took another step too big. Okay. So the last thing we did was the 3 rights, right? So let's take a look. 1 down should push all 4 boxes and 2 downs should not. So let's take the 2 down version. Okay, so that's the 2 down version. So again, we're going to skip you. Not yet. We'll take the 2 down version. And see, this is why I like this style of TDD, because we're basically, incrementally giving more and more data into our algorithm, and we'll find our bugs individually, hopefully. All right, so 2 down should look like this. Okay, so there's 2 down. Let's see if we can figure out what's going on here. So we broke 2 down because we never moved. Now, why did we never move? That's interesting. I don't know why we didn't move. Because down should have moved us. Down did not move us down. All right. So we know that we can move into a dot. Or we can try and recurse back and figure out what's going on. I admit to being curious about exactly what's going on here. Why did we fail to move down? Let's do a little console write line. Trying to move from row column to row plus d row, column plus plus D column. So that's we're going to print that out. And then, so we'll start printing out some help here, right? So we'll say this console right line failed wall. Okay. And if we came down here, then we're going to say console right line success. And then our message here will be based on whether adjacent was a dot, right? So we'll say adjacent is a dot. If that's the case, then we're going to say we had empty space. And then otherwise we'll say we pushed. Okay, and that'll be that, except of course C# does not let you use ternaries inside of that kind of thing unless you actually put it in parentheses for reasons I don't understand, but I'm sure a language person could tell me. And then what do we write here? Console right line probably failed, could not push. Okay. Let's run this. Okay, so here, yeah, we're running a bunch of tests with a bunch of data. Let's skip these. Actually, the easiest way to skip these is just comment everything out. It'll take less time. Comment everything out except the one I care about, which is that one. Okay, run this. Okay, so trying to move from 2.2 to 2.1, we failed because of the wall. So let's go back and look at this. Right? Go back and look at this and understand exactly what's happening here. Right? So, whoops, I wanted this and this. And I'm going to cut that out. I'm going to put you over here like this. So we tried to move from 2.2 to 2.1, we failed because of the wall. That makes sense. So then we tried to move from 2.2 to 1.2. Right, so that was this. Tried to move to 2.2 to 1.2, and that was success because it was empty. Tried to move from 1.2 to 0.2, we failed because of the wall. Sure. And then we tried to move from 1.2 to 1.3. We have a success empty because we had a success pushed. Well, that's kind of a weird how that printed out, but all that's basically trying to tell us is, yeah, we're printing things in weird orders. Which is fine. Because when we tried to move from 1.2 to 1.3, that meant we had to move from 1.3 to 1.4, and that was a success because of this empty, right? Because we were here, right? So 1.3 to 1.4, that was a success because of this empty, and then we have a success here because we pushed. So yeah, they're just in weird orders. So here, trying to move from 1.2 to 1.3. Right, so move from 1.2 to 1.3. That is weird. Why is the robot still here? The robot should have moved. All right, the robot should have moved. Even though we got the right answer, like looking at this output now, we're seeing something strange. Okay, so if the adjacent was this, or we tried to move and we were able to move things, then we need to put a dot where we are, and whatever we are needs to go in the current spot. That is weird. We're going to do right line for all of this so that we get things, yeah, because they're going to be interleaved, right? And we'll just indent these a little bit. Okay, let's see if we understand here. So current adjacent fail because of the wall. Your adjacent is a dot. Then we do this. Or if we tried to move, then we do this. But that should have returned true out of this move, which says that the robot should have moved. Yeah, that's weird, right? Let's go ahead and console right line the thing here. See if we can see what's going on in each step. See if we can figure out where the problem is. Okay, so we failed the wall. We succeeded because we were empty. We failed because of the wall. We succeeded because we're empty. So this is the push of the O, and this is the push. Right, this succeeded because of pushed. So that looks okay. So then every step here is we move the O, we move the O, we move the at. That was a success. And we successful because we pushed, right? So success empty, success push, success push, success push. That looks correct. Now we're trying to move from 1, 2 to 1, 3. So this is like the robot position has not been updated. This is the part I'm very confused by. We are overriding the robot. We are reusing the robot. It is trying to move things that are incorrect. The robot is a row and a column. So if we were able to move the robot from the row and a column with the D row and D column, then the robot is now in D row, D column. We are hitting this line, right? Oops, we're in select. Okay, so this is our first move, right? So let's take a look at, let's get rid of all of these. Let's get rid of, come on, get rid of all of these. Why won't you delete? Nobody knows why you won't delete. Oh, because that's locals, because you're being dumb. You care about this. Okay. So let's see what the robot is, and then let's see what D row, D column is. All right. So we tried to move left from 2, 2. So let's go take a look at our output. So this was, or tried to move up from 2, 2 to 1, 2. So that was a success. So we moved the robot. Okay, and then from 1, 2, we're trying to move it right. And that was a success. So the robot should now become 1, 3. And why did it not become 1, 3? I really am confused by that. This feels like a bug. Is this new row is robot row plus D row? New column is robot column plus D column. Oh my God, I just see it. I see it right now. I put row here. Yay, so he can move up and down, but he couldn't move left and right. Never mind. Confusion is Brad. Brad did a dumb. All right. So our test passes now. That's great. All right. Let's get rid of all these console right lines. We'll leave them in here for now, just in case we need to, debug some more. But I'm feeling a little bit confident about what's going on here. All right. We can go ahead and uncomment all of these tests now. We had commented out because we didn't want to look at a ton of console output. Does our final version work? Our final version works. Okay, so we have one more piece of data, which is this is our big example, right? So that's a ton of instructions across multiple lines. So this is going to be our final piece of data here. I just realized why it wasn't doing this for me, because I had done something dumb. So there's our data, our bigger board, but our huge set of instructions, and I missed the edge there. And then here we need what we know to be the final state. That's this, the final state of all of those instructions. We have pretty good confidence now that we're doing the right thing, but this is our big insurance ticket, right? Okay, that looks good. So the last thing we need to do is we need to now take this and compute the GPS value. Right, so this is what we're going to want to do with this. This test is going to look pretty much like this test. To start with, our input is file, read all text from the file name. But the end result is assert equal expected storage room dot GPS value. That's what we care about now, right? So we need to compute the GPS value. Let's do a get. This is computationally expensive enough. We shouldn't put it in a property. So now we need to get the GPS value. Let's go ahead and roll these tests up so I don't keep scrolling by them. We need to get GPS value. That would go here. Public int get GPS value. And our GPS value was constructed by 100 times the distance from the top plus the distance from the left. Okay, so we're going to write our classic grid walk here. We need a result. We're going to return the result when we're done. If get node for row and column is a box, and result plus equals row times 100 plus the column, and we will return the result. Right, and then down here, that should be 10,092. So data1.txt is our big version, right? And so this should be 10,092 if we've done everything correctly. And it looks like we have. I mean, the math part of it's fairly simple, right? So our big version looks like this. It appears to be, looks like, that's 50. So it's probably a 50 by 50 room. It is 50 by 50 room. And looks like 20 lines worth of 1,000 characters. So we have to do 200,000 moves. So a lot, but still, I think, fairly reasonable. Fingers crossed, and we get the right answer. Okay, very good. All right, so second half. Lanternfish user information. Oh, yeah, there's a second warehouse robot that's also malfunctioning. This warehouse's layout is surprisingly similar to the one you just helped. One key difference, everything except the robot is twice as wide. The robot's list of movements don't change. To get wider warehouse map, start with the original map, and for each tile, make the following changes. Okay. This will produce a new warehouse map that's twice as wide and with wide boxes that are represented by open, close, square bracket. Robot does not change size. So the robot stays in the left-hand side of the doubled up space. Everything else doubles up. O's become square brackets. Okay, so this is the larger example now, except you can see now we have double wide walls on every side, right? And we have a robot here. Because boxes are now twice as wide, but the robot is still the same size and speed. Boxes can be aligned such that they directly push two other boxes at once. For example, consider this situation. So here's another situation. After appropriately resizing this map, the robot will push around the boxes as follows. So here's the initial state, and here's a move. You can see the boxes are half overlined with each other. Then we move down, we move down, we move left, we move left, we move up, which you can see pushes all three boxes up, right? Because it's pushing on this box, and this box tries to move. Tries to move up, and it can't move up because the edge of this box is against this pillar. So it moves left, moves up, pushes this one box up. All right, so we've got another set of states for the new version of the grid, which is a double wide grid. So let's start then with this as our input data. Okay. So now we're going to go back to storage room tests, and we're going to collapse these into a new subclass, which is called single wide. Right. And then that will be all of our single wide tests. And now the benefit of that is we can collapse that and make it go away, which is great. So collapse the single wide. Now we'll start writing our double wide tests. All right, so in theory, our input looks like this. Looks like this. Okay. And we're going to make one maneuver out of that. And we want the result to look like this after one move. Right? We can also make sure we can actually start with the initial state, because the initial state now looks different from what we had before. So let's try and do that, which would be no moves. We don't really know if that's going to work, but we'll try no moves and see what happens, right? I think that should work because it'll just be an empty string, so our character array will be empty, right? So that's what our exploded version should look like. All right, so can move in double wide space. All right, so we have our inputs and we have our expected, I forget what we call it. Expected grid is fine. Okay, just like before, our room is going to be a new storage room, right? With our inputs, we are going to, we're going to perform the movements, and then we're going to say assert equal to the expected output, the expected grid will be the room toString. Strom. I don't know what I'm thinking there. Okay. We haven't done anything for double wide yet, so we expect this to fail, right? Because it's still going to look like this when we go in. And we want it to look like this when we come out. We are testing at least one thing right now, which is that no movements is okay. And, all right, we want to do this as object and not as string, because that's more visually helpful for us. We expected this, but we got this. So we did not do a double wide conversion. However, we managed to not move anywhere, which is good because the first move would have been a move left. All right, so the storage room then can just basically say double wide. Double wide is true. So then we'll come up here to the constructor for the storage room and take an optional double wide, which will be false by default. Okay, let's make sure we didn't break anything just by adding that parameter other than the thing we're still trying to fix. Okay, that looks good. We didn't break anybody. So if we're double wide, what does that mean? Well, it means we have to go through the grid. Grid is going to be grid, select row. And then we're going to say row select node. So for each node, we're going to do a node select, node switch, sorry. And then we'll do a list here, right? And this is going to turn, let's see, we're going to turn this into, this into this, right? We're going to turn at into at dots. We're going to turn wall into double wall, and we're going to turn the box into the box. And then anything else, how did we get here? Row, new, invalid operation exception. Okay. So this select is going to turn an enumerable of characters into an enumerable of strings. So we need to string join all of those together so that we get a string, right? And then we're going to return that into an array. We're going to return that into an array. So that array is going to give us a string array. Wait a minute. So this string join, why can't I turn this into a character array? Because that's really what I want, 2 character array. Because the result of string join is going to be a string. Well, the string 1, 2, 1. So that select. After that select, we need a character array. I had missing a parenthesis. And then this whole thing needs to be turned into an array. Okay, there we go. Now we got our grid turning double wide. I believe that that should be all we need here to get our first test to pass. And it is. Okay, so we have doubled our space now. All right, so what is the next test? The next test is we're going to move left 1, right? So let's go ahead and move left 1. That's this as our input. Inline data. That's this as our input to move left 1. And then the resulting output should look like this. That's interesting. So here's the question. Should we expect this to work or not? Let's see. It did work. So why did it work? Well, it worked because none of our logic for movement cares about O. All it knows is space is somewhere I can move to. Hash is somewhere I cannot move to, right? And so it literally treated this as though it were 4 O's in essence, right? And it moved each one left 1 space. That's pretty good. Okay, so that is not what I wanted. This is the browser I wanted here. Okay, so if I move down, move left, move up. So this is the first time that we're doing something interesting because all of this is empty space. So let's get all the way to move up. Okay, so let's get all the way to move up. And stop it. Yes, you can all see how I did. All right, so the next one is this. Inline data. So we're going to move up. And then the result of that is moving up is going to have pushed all of those boxes up. That's clearly not going to work as is, because obviously that's not what we have written. And let's watch that fail. Let's see what it does, see if we can reason about what it did. That makes sense, right? Because instead of pushing all the boxes up, right, it pushed just the right-hand side of this box up and the left-hand side of this box up because it doesn't understand boxes as being entities all of their own. So what that means is from a push perspective now, we need to know if you're trying to push a box up or down because they're only double wide, they're not double tall. If they were double tall, we'd have to worry about left and right as well, but they're only double wide. So up and down is really what we care about. And if we think about, what it means to move boxes that look like an arrangement like this, and the @ character is sitting right here, for example, that we are trying to push this box, which means this box needs to look on both sides of it and see what it needs to push, which means it needs to push this box and this box as a result. But when things are double wide, things get a little more complicated. So let's go see what we need to do here in our move. So we already know that if the adjacent is a wall is a failure is fine. But we can't just do this because that's not enough, right? So we're going to do 2 things here. To make this easy, because the push is easier if we always try and push a box from its left-hand side, we're going to say if your adjacent is the right-hand side of the box, right, and decall is 0, then we're just going to try and move row and move 1 left. Okay. That's just going to make all the math or all of the logic about all of this much easier. So now what we're going to say is if you're trying to move the left-hand side of a box and you're trying to move it up or down, what do we do then? Well, we need to look at both halves of the box and we need to look up in both directions and see what's going on, right? So from this perspective, we need to look, above 2 in essence for our for what we decide to do. All right, so we're going to say above left is going to be get node of row plus d row plus 1. Row plus 2 times d row. I don't know why I did a plus 1 there. And then we know the column's not moving, right? And then above right is going to be this. So depending on what's above it. Oh, and actually, we're not looking at it. I'm sorry. I sent us down the wrong path here. We shouldn't be looking at adjacent. We should be looking at current, not adjacent. So we can just do adjacent right is get node of row plus d row and then column plus 1. Okay. Now what we want to do is we want to know how to move this thing based on what's above it, right? So we're going to do adjacent and adjacent right switch, right? We're going to do another one of these, right? So if you have a dot and a dot above you, then you're just ready to go. If you have, we're going to assume, by the way, that you can't move by default, right? So what are the 4 cases that we're concerned with? We have above us, we have a box starting on the right. We need to do something. We don't know what that is yet. And then we have a case where we have a box on the right-hand side of a box with nothing above it. Nothing above it on the right-hand side. And then the last case is we're sitting with 2 boxes above us, right? In which case we want to do something else. So those are basically the 4 cases in which we think we can move things, right? So either there's dead space above us, which is good, or there's boxes above us, either a box on our right-hand edge, a box on our left-hand edge, or 2 boxes on our left-hand edge and right-hand edge. So for this, our success would be if we try to move, we're going to say row plus d row plus d row, and the column that we're going to move is column plus 1, right? Because that's the one on the right-hand side. Okay, so that's our success there. And then, of course, we need to pass d row decal again. And then we also need to move, this time we're going to do row plus d row. And we do column minus, or just column, right? Just column. So then, is that right? Yeah, well, we'll figure it out. And then here we need to do both. We need to do both of these things. Actually, we want column minus 1. Because column minus 1 will put us on the other edge of the box. There's no reason for us to come through and hit this and add an extra level of recursion. So if we've got both of these, and we'll go ahead and we'll do both of these. Okay. So here's the interesting thing about all of this, right? So we're going to try and move things. In our version where we have either pretty cut and dried success or cut and dried failure, we either move things or we don't. But here we have the possibility of moving one thing and not the other thing successfully, right? Which is bad, right? We don't want to half move things. So what we're going to do then is we're going to take a copy of our grid, right? So this is going to be grid select row. We're going to do row 2 array. 2 array. This is basically a deep copy of this double array. If we did clone here, grid.clone, we'd get a shallow copy, and we need this inner copy as well. So this is our grid copy. All right. So then we're going to say, if we were successful, we're going to do something. But more importantly, if we weren't successful, then the grid copy goes back into the grid because we want to undo all the changes we just did, right? And return false. So up here, we're going to do something, and then we're going to return true. And the something we're going to do is the equivalent of this, except we need to do it twice, right? Because we have the box. So we're going to take current. We're going to need to know, let's see, we could do it like this. If we do it like this, because we're going to do column plus 1, right? We don't need decall, because we know decall's not manipulating anybody. We also need to do a column plus 1 over here. And for that, we're going to get the current node of row and column plus 1. We don't have that anywhere yet. So we move ourselves up or down, whichever it is, both sides. And then we put dots in our place. Okay. I think that should be it. That seems like it should move things along. Let's go ahead and see what happens here. Okay, that looks like it did it. So, this is really kind of where, updating the algorithm inside. None of our other tests are failing. They're all still running. And we have basically made it so the thing can work in either single wide or double wide mode, right? So let's go ahead and, trusting that we have done the right thing all over, let's go ahead and try this. Even though, that didn't really work out for us very well last time. All right, so here's our last test we're going to put in here, right? So inline data, and we'll see if this works. And if it doesn't, we'll take smaller steps, just like we did before. And then let's see what the end result should be. The end result should be, after a bunch of moves, this should be our end result. And I think if we got here, then we're fairly confident that we have correctly moved boxes around and everything is good to go. So let's go ahead and run this test and see. And that test does work. So then the last thing we need to do is we need to run the tests with double wide. So here it's going to be exactly like this, except double wide is now true, right? And what we're going to see is we're going to get back 0 because, of course, oh yeah, we need to run the tests. We're going to get back 0 because our GPS calculation right now is based on looking for O's. And in a double wide case, we don't have any O's, right? So let's go back and let's look and see what it tells us about calculating GPS. Some of these boxes GPS, let's see, it says warehouse also uses GPS. For larger boxes, distances are measured from the edge of the map to the closest edge of the box in question. So that means when we're measuring from the left, we're actually looking for the open square brackets. Okay. So in this case, it's 100 times 1 because you're down 1, and 5 because here's 0, right? So 0, 1, 2, 3, 4, 5. Okay. So the other thing we have to do to get our GPS calculation correct should be, let's go ahead and roll you up because we're just going to keep scrolling by you. All right, so our GPS calculation then, we just need to add this. We just need to say an O or a square bracket, open square bracket is our calculation point. So if we run that, we get 9808 instead of 9021. That's really surprising. So in the scaled up version of the larger example, we have this. So obviously we've done something wrong. So let's use their sampled data from, this is the big sample all the way up at the top, So we're going to do this. Oh, wait a minute. No, it wasn't this sample. They gave us a new sample, didn't they? They gave us a new sample. Larger example before would now look like this. Larger example before, maybe it was the same thing. Okay, so the larger example from before, that's going to be this. Okay, so we have apparently at least one more test for double wide. Inline data. Okay. What should you look like? You should look like this over here. Down. Come on, Edge. I click. We go. Scaled up version of the larger example from above. After the robot has finished all its moves, the warehouse would look like this. Let's see if the warehouse looks like that. See if we have messed up the box movement or if we've messed up the GPS calculation. One of the two. Okay, so we did not get it to look like that at all. That is interesting. All right. I guess what we're going to have to do then is we're going to watch, right? We're going to go ahead and comment out all of this inline data because I really just want to run this one. Really just want to run this one. And we're going to take this as our method name. All right, so one of the things we can do with the command line prompt here, come on, launch profiles. We're going to run just that method. That's all we care about. So now we should have one test running and failing. We do. Okay. So the easiest way for us to sort of think about this is to visualize it. All right, which is a good reason why we didn't need to remove all of our console write lines. So after every successful move, what we really want to do is print out everything, right? So we'll say console write line after direction. Oh no, we don't know the direction. We only know D-row decal. So we'll say after single move, because I really want to know which success case we got into, right? And then this is a double move, so we'll say after double move. We'll do that. And then we will console write line again. Grid. We're also going to do a console read key because I want to pause after each step and make sure that we're doing the right thing. And maybe we can visually see what's going on rather than stepping through the code. So we can console write line instruction is instruction from row, from robot row, and robot column. So that's how we can see our instruction. All right, so let's run this now. So after a single move, we should have looked at the initial state too. This is my bad. So we will console write line toString. We're also going to console write line in between all those. So we're going to say console write line initial state. All right, so everywhere we console write line the game board, we'll add an extra write line just so we get blank lines in between everybody. Okay, so let's do Control F5 again. So there's our initial state. We're trying to move left. So we've got a single move, and we've got a single move, so that moves the box in its entirety, and then we move the robot. So that's good. So our next instruction is down, and then we have a single move, and then that's it. Down, single move, and then that's it. So far, so good. Right, single move, moves the box, moves the robot. Up, okay, left, down, up, right, down, right. Okay. And then we got single move up, single move down, single move down, single move up, single move down. We got a right, which pushes that box. We've got a left. We've got a right. We had a down, which went nowhere. We had an up, which went nowhere. The up shouldn't have gone nowhere. The up should have been fine. That's interesting. Right, so we saw this where the down went nowhere because this box, right? So we're here, we try to go down, we can't go anywhere. We try and go left, and that's okay. We try and go right, and that's okay. We tried to go down, and that failed. We tried to go up, and that failed, but that shouldn't have failed. Why did that fail? That is a good question. Okay. That's a test we can try on our own, right? So let's take, oh no, it's really actually hard for us to start with a double wide, isn't it? Yeah, that's tough. Let's see if we can find this version of up from 710. Let's set a breakpoint on that. Okay. Let's go to here. All right. We'll go to here. And we'll set a condition on this breakpoint, which is that the instruction is up and robot is 7.5. That's what we said. 710. Sorry, 710. Robot is 710. All right, so that's our condition. So let's go ahead and close that. Let's hit the breakpoint. These are all going to be okay. All right, moves there, moves up, down, up, left. All right, the down fails, the left is okay, the right is okay, and then here's our up. Let's see if we can figure out what's going on here with up. Well, let's step in here, and we'll say the current is our robot, right, obviously. The adjacent is, we don't know what it is yet. The adjacent is the left-hand side of the box. That makes sense, right? Because we have the left-hand side of the box above us. Let's not care about those so much. Let's care about row and column, row plus D row, column plus D column, just so we know what direction we're going, right? So we're trying to move that up. Okay, so that looks good. So the adjacent is not a wall. Okay. So the current is not a right-hand side of a box. It is a left-hand side of a box. D column is 0. Why didn't we go in there? Oh, current is not. Wait a minute. Oh, no, that's, Right, that is weird. So we're going to come down here. So this then isn't right. This single move isn't right because we just do a straight try move here. Right? So it's going to try and move just one thing. Which is interesting because, right? Can't just, yeah, no, actually that should be okay. So we're going to try move this, right? That's going to step right back up into here. And what we should now see is that we're able to now, we're going to try and move from 610 to 510, right? Because adjacent is not dot. Okay, so that's good. We stop here. So now we're trying to move 610 to 510, right? So the current is the left-hand side of the box. The adjacent is another left-hand side of the box. So now we step in here. We're trying to move that box. Our adjacent right is going to be the other side of the box, okay? So we have a box above us. Oh, we never took into account a box being directly above us. Sure, that makes sense, right? This just falls directly into false. All right, so if we have a box directly above us, then all we need to do is we need to try move row plus d row and our column, and d row, d column, because we're looking at the left-hand side of a box already, so we just go ahead and try and move the left-hand side of the box. All right, let's just run this instead of debugging it. And this time, what we should see is this thing is going to move up, down, up, and move that one to the right. That's good. Left, right. Now, when we try and move up, we're going to move that box. We're going to move that box. We're going to move ourselves. Move down. We're going to move left. Going to move down, left, up, down. All this looks okay. We move up. That moves the box. That moves us. That moves the box and moves us. All right, just bouncing around for fun. Nobody knows why. Okay. Gonna get all the way over here. We're gonna end up pushing those boxes up, I assume, at some point. So there's the box, box, us. Box, box, us. Box, box, us. Box, box, us. All right, I'm fairly convinced at this point that we're doing the right thing. Let's take our console output back away. All right. Whoops. Our console output back away. Where else do we see console output? None up here. Just up here. Okay. And this. We don't need this either. Okay. Okay, so good. We got our answer. We got ourselves in the right spot. That's a good sign. And this one also passed because this is also still running. So now, if we take our big map, do we get the answer that we want? And the answer is you got to run all the tests, which means I don't know if we actually got the right answer last time because we weren't running that test. We're only running that one data item. Come back. Okay, so now we got the correct answer. So there we go. That was more debugging than I expected, but not super surprising. I mean, if we actually look at my score from yesterday, you'll see that what ended up happening is I finished the first part in 26 minutes, and it took me 2 hours and 10 minutes to finish the second part, which is actually not that surprising given the complexity of the problem. Like, I spent a lot of time struggling on getting the box movement right. It was actually much harder yesterday than it was today, to the point where I stopped and took a break, which is actually not all that uncommon for me. Like, you feel like you're stuck, fine. Walk away from it, think about it in the back of your mind and not in the front of your mind. So I think I stepped away and watched, 22 minutes of a sitcom, and then came back to it and said, oh, I think I understand what's going on. And so that's what happened here. So I think that's going to be it for today. As you noticed, we skipped 3 days. What that meant was I wasn't sure if we were coming back. So once again, I'll warn you, this may be the last video because we're really only going to be making videos when I think there's an interesting evolution of the algorithm that we can get to it with TDD. So anyway, that's it for day 15. Thanks for tuning in, and hopefully I'll see you next time.